Hello, everyone. Welcome back. Today, I'm going to be talking about the graphs of rational functions. Okay, so here it says with vertical asymptotes, the graph of f of x has a vertical asymptote at x equals a if one of the following limit statements holds true. That as x approaches a from the right, the limit as x approaches a from the right is plus or minus infinity, or if the limit as x approaches a from the left, it's plus or minus infinity as well. Now, we haven't really gone over limits, is the thing. Limits is the first topic you'll learn in your calculus class, not in this class. So I want to kind of translate this to English. What does this actually mean? It basically means that there is an asymptote there if, as we're approaching that asymptote from the left or the right, that certain value from the left or the right, I'll give a quick demonstration here. So let's say we have asymptote here at x equals a. If we're going like this, right, then as we're approaching with respect to x, as we're approaching the asymptote, y is going up to infinity, right? Y is going really, really high. Or the opposite could be true. Maybe it's going like this, downwards. It's going towards negative infinity as we approach a. Or those things could also be true from the left. So it could be something like this, that sort of thing. And we already kind of know this a little bit from some work we did the last time, right? A couple days ago, we were drawing some graphs of some rational functions. Well, actually, I guess not some rational functions, just reciprocal functions. And you'll notice that whenever we had a vertical asymptote, we always had a line approaching infinity or negative infinity with respect to y as we were approaching that asymptote with respect to x. And that's true here, here, and here too, right? So we have kind of seen this phenomenon a little bit, but we haven't really explored it properly with all rational functions. We kind of just did it with specifically reciprocal functions, which is where we have one over a function. In this case, we're going to talk about it with rational functions, where we can have function over function. So all reciprocal functions are also rational functions, but not all rational functions are also reciprocal functions. So let's go ahead. Let's go ahead and start with this one here. So this one here says, for this function, determine all possible asymptotes and sketch the function. Well, let's remind ourselves really quick, what are the asymptote rules? We discussed this in the last time. Basically, for vertical asymptotes, if we have a 0 in our denominator, that's where the vertical asymptote is, at the place where x, where the denominator would be 0. That the only exception to that though is if it cancels out with something from the top. If it's also something where the numerator would also equal 0 at the same point, then it's actually a hole there as opposed to an asymptote. So that's the exception to that. As for a horizontal asymptote, that occurs depending on the degree of numerator versus denominator. So if the degree of the numerator is greater, then that means that there is no horizontal asymptote. If the degree of the denominator is higher than the degree of the numerator, it means we have the asymptote is at y is 0. And if the degrees are the same, then that means we just take the coefficient over coefficient, and that's going to be our horizontal asymptote with just the leading coefficients there. And then for oblique asymptotes, these occur if and only if the degree of the numerator is exactly 1 higher than the degree of the denominator. And then to find the oblique asymptote, we use our long division method that we learned in the last unit. So there we go. So actually I did a whole lesson about those in the last lesson where we just strictly go over finding asymptotes. So do make sure to familiarize yourself with that if it's not something you're already familiar with. So let's start with vertical asymptotes. Are there any vertical asymptotes here? Yes, there are, right? There is. There is one at x is equal to 3. Okay, so at x equals to 3, we have a vertical asymptote because that is where our function would have a denominator of 0, and that cannot be canceled out with a numerator of 4. 4 is not the same as x minus 3. Okay, what about horizontal asymptote? Well, it looks like in this case, the degree of the numerator is 0 and the degree of the denominator is 1, so degree of the denominator is higher, which means our horizontal asymptote is going to be at y is equal to 0. I'm having trouble writing today for some reason. Okay, so there we go. Those are our asymptotes. And then it also tells us to sketch this function. So let's sketch this function. So we have a horizontal asymptote right here at y equals to 0. And then we have a vertical asymptote at x equals to 3. Okay, that's better. Good. Okay, and now we need to determine how to sketch this function. Well, how do we sketch the function? Well, we're just going to plug in a number that is after the asymptote of x equals 3 and a number that's before it to kind of figure out the direction of this. So what if we plug in 4? We'll get 4 minus 3, which is 1 in the bottom, and then on the top we'll have 4, right? So if we do y equals 4 over 4 minus 3, right? Because in the case where x is equal to 4, we're going to end up with 4 over 1, which is 4. So therefore, we have a point at 4, 4, right there like that. And then what about something where we have that's less, right? What about 3, for example? Well, 3 we can't do because it's the asymptote. What about something less than 3, like 2? What would y be when x is 2? This would be equal to 4 over 2 minus 3, which is 4 over negative 1, which is negative 4, okay? So therefore we have 2, negative 4 like that, and that's where another point is. And then we're going to draw this function. We're going to draw this function, and it looks somewhat like that. There we go. All right, let's try the next one. It says for the function negative 2x plus 4 over x minus 3, determine all possible asymptotes and sketch the function. So let's start with vertical asymptotes. Well, there is a vertical asymptote at x equals to 3, similar to the last one, right? We have the same denominator here, and we still can't cancel this denominator with anything in our numerator, even if we were to factor it or anything like that. We can't do that. Okay, now what about the horizontal asymptote? Well, what is the horizontal asymptote? Well, in this case, the degrees are the same. It's linear over linear, right? Which means what? Which means that we just take the coefficients of the leading coefficients. So for leading coefficient for the top is negative 2, and then for the bottom it's 1, right? X is the same as 1x. So the horizontal asymptote is at negative 2 over 1, which is just negative 2. Okay, so now let's draw our asymptotes. So y is equal to minus 2 for our asymptote, so like that. And then we have x is 3, like that. Awesome. Okay, so now we're going to do a point that is after 3, so a point like 4. So what's y equal to at x is 4? That would be negative 2 times 4 plus 4 over 4 minus 3, which is just going to be negative 8 plus 4 over 1, which is just going to be negative 4. So therefore, the answer is 4, negative 4 for this one. So we have a point here, so we're expecting, so there we go, we're going to just go like that, now that we have that point, because it's going to approach the asymptotes. Okay, then let's do the same thing with something less than 3, so maybe let's do 2. So that would be negative 2 times 2 plus 4 over 2 minus 3, which is negative 4 plus 4 over negative 1, which is 0 over negative 1, which is 0. And just a reminder, 0 is okay for our numerator. It's just our denominator that can't be 0. So this is a perfectly good and valid point. So this is all good. Awesome. All right. So we have 2 and 0. So we have a point right there. So then that's going to just approach, oh, that's not a good line. I'll try to do that a little bit more accurately here. There we go. Awesome. Okay, let's try this one. It says example 3. Determine all possible asymptotes and sketch the function. Oh, this is kind of cut off in a strange place here. I'm going to put this on a separate page. Hold on a sec here. Okay, so let's try this one next. So it says determine all possible asymptotes and sketch the function. Okay, so this one, it looks suspiciously like we might be able to factor this and get some common factors. So let's see if we can. Y equals 4 times x minus 1 over 2 times x minus 1, which means y is equal to 4 over 2, because we can cancel the x minus 1s, which means y equals 2. So because the numerator and denominator ended up canceling, we don't have an asymptote at x equals 1. We have a whole at x equals to 1 instead of an asymptote. So we don't have any vertical asymptotes. And furthermore, we don't actually have any asymptotes because this equation simplified to y equals 2. And as we know, y equals 2 is a line. And when has a line, when has a y equals mx plus b, or in this case, a y equals b, when has an equation like that ever had an asymptote? Well, never. We know that polynomial functions in general never have asymptotes. We learned that last unit. And furthermore, we learned in grade 9, we never learned about asymptotes in grade 9 or grade 8 when we learned about lines, because lines don't have asymptotes. And so we don't have to worry about any asymptotes here because the equation we were given turned out to just be the equation of a line with a hole in it. And that's it. So let's draw the graph. Let's see, here is 2, x and y, and let's just like that. Awesome. So we have a hole at 1, and there we go. All right. So there we go. Oh, that kind of makes it look like 20. Shoot, I don't want to be misleading there. I'm just, yeah, I'll put this over here. This is 2. I think hopefully that's more clear. But no, it's not 20. This is that circle there is a hole showing that at x equals 1, we have a hole in this line, because if we were to, in the original function, put 1, we would get 0 over 0, and of course that's not valid. We can't have that. But yeah, so there we go. All right, let's do the next one here. This one's also kind of placed awkwardly, so I'm going to paste it on the other page. Okay. So, for this function, determine all possible asymptotes and sketch the function. Well, I'm just noticing here we can definitely factor the denominator because it's a difference of squares, right? Y is equal to 3 over x minus 2, x plus 2. And looks like x minus 2 and x plus 2, unfortunately, they cannot cancel out with our top. So that means that anything that the denominator, any x value that would make the denominator 0, is going to be the true asymptotes. So the vertical asymptotes are the zeros of the denominator, which is x equals to 2 and x equals to negative 2. What about horizontal asymptotes? Well, what's the degree of the denominator? The degree of the denominator is 0, right? It's just 3. And the degree of the denominator is 2, right? We have x squared. So what does it mean when the degree of the denominator is greater? It means that the horizontal asymptote is y equals 0. And now we're done, because we know that if we have a horizontal asymptote, we can't also have an oblique asymptote. So we can forget about oblique asymptotes. And we also know, by the way, too, something I mentioned last time, maybe the time before as well, is that with vertical asymptotes, we can have as many as up to the vertical asymptotes we can have. It's up to the number of degrees that are in the denominator. So if the denominator is degree 5, we could have up to 5 vertical asymptotes, right? Because it's all about the number of zeros in the denominator, and the maximum number of zeros for any given polynomial function is equal to the degree of that function, right? So a quadratic maximum it can have is 2, right? A cubic function maximum zeros it can have is 3. So that gets translated to asymptotes here. As for horizontal asymptotes and oblique asymptotes, we can either have neither of those two. It's possible to not have any, but it's possible to just have one or the other, but not both. and it's also not possible to have more than one horizontal asymptote or more than one oblique asymptote. So for purposes of this course, we can have as many vertical asymptotes as depending on the degree of the denominator. But as for horizontal asymptotes and vertical asymptotes, we either don't have either of them or we have one of just one of them, and those are the only options. So as soon as we have a horizontal asymptote, we can't have another horizontal asymptote or an oblique asymptote, or vice versa. As soon as we have an oblique asymptote, we can't have another oblique or a horizontal asymptote at all. Okay, so moving forward with that. Excellent. Okay, so let's put in our asymptotes. So we have an asymptote here. We also have an asymptote here. Asymptote. Okay, and then we also have one at y equals to 0 right there. And then let's sketch this. So how will we sketch this? We're going to say, well, what is this function when x is 0? Or when y is 0, or yeah, when x is 0, sorry. Let's start with that. We'll get 3 over negative 2 times 2, which is negative 3/4. So we have a point at 0 and negative 3/4. So we're going to have our first part of this kind of go like that. And then we're going to choose a point that is less than negative 2. So I'm going to choose negative 3. So we're going to get 3, negative 3 minus 2, negative 3 plus 2, which is equal to 3 over negative 5 times negative 1, which is 3 over 5. Awesome. So we have a point at negative 3 over 5. And then we'll go like that. And then we'll do that. And then we're also going to end up with, I think, the same thing actually. Yep, we're going to end up with 3 over 5 again. So we're going to get 3 and then 3 over 5 again like that. And then let's draw that there, approaching those asymptotes. And there we go. Awesome. Okay, let's do one more. Yeah, we just have one more to do, and this one's also kind of awkwardly put on the page, so I'm going to switch it up here in a moment here. Okay. So for this one, I noticed that we can factor, so I am going to factor here. So here we would have y equals x minus 2, x plus 2 over x minus 1. Okay, well, I tried factoring and actually turned out that we're not able to cancel anything out. But it's still good to factor and try because you never know what is going to cancel out with something else and what is not, right? So in this case, nothing did, and so we're good. Now, where are our asymptotes then? We have a vertical asymptote at x equals to 1. And what about a horizontal asymptote? Well, the degree of the numerator is 2, which is higher than the degree of the denominator, which is 1, so therefore we have no horizontal asymptotes. So do we have an oblique asymptote? Is the degree of the numerator exactly 1 more than the degree of the denominator? And the answer is yes. Yes, there is. Or yes, it is, rather. Okay, so therefore, we do have an oblique asymptote, and we've actually got to find the, we have to do long division in order to find the oblique asymptote. Okay, so let's do it. So we have x squared minus 0x, or I guess plus 0x minus 4, right? I'm grabbing our original function, and we're going to put x minus 1 here, and let's use long division. So how many times does x go into x squared? Well, x times. Then we get x squared minus x. Then we subtract, and we get x. How many times does x go into x? Well, once, right? And then we get x minus 1. And then we subtract, And then we get as our remainder, oh, not that the remainder even matters, but technically as our remainder we get minus 3. So therefore our oblique asymptote is going to be at x, y equals x plus 1. Okay, so now let's draw this function. Let's look to drawing this. Okay, so let's do y equals x plus 1. So here's our y equals x plus 1 line. And then our vertical asymptote was x equals 1. So I'm going to draw it like that. There we go. And then we're going to draw some other points in this. So let's figure out a point that is to the left of our oblique asymptote. Okay, so let's try minus 2. Minus 2. What do we get if we put in minus 2? Well, let's see. We will get minus 2 squared minus 4 over minus 2 minus 1, which is 0 over negative 3, which is 0. So we have a point at negative 2, 0, so a point there. And then what about at positive 2? We would also get 0, right? We would get the same exact thing. We'd get 2 squared minus 4 over 2 minus 1, which is going to be 0 over 3, which is still 0. So we have another point over here. And then those points are going to approach our asymptotes, right? As we know, that's what these points are going to do. They always approach the asymptote. So let's just draw them approaching those asymptotes like that. Awesome. All right, well, that is that. Good work, everyone. And I will see everybody next day. Bye, everyone.